We spoke about the fast Fourier transform and how that can help us, especially where there is no transitivity. Now, what I want to do now is actually to warm us up is look at a couple of different examples of relations, of equality, of matching relations that are not equivalence relations, and so that we may not be able to use the automata methods or witness table methods. And let's see how we can handle these things. So let's start with an easy one. And we're looking now at the not equal. In other words, we're going to say that string S matches string T if Si is not equal to Ti for all I. In other words, it's the opposite of what we're looking for. Obviously, this thing is not transitive, because if A is not equal to B and B is not equal to C, it doesn't mean that C is not equal to A. C could be equal to A. So it's not transitive, and it doesn't seem like we'd be able to do anything with it that way. The question is, what can we do with it? And let me also, in order to even show you how amazing this particular example is, let me start by asking you the following question. Like I told you yesterday, sometimes in pattern matching, when presented with a problem, the thing that we like to do is consider the binary alphabet case. So let's consider this problem. Over binary alphabet. So let me give you a couple of minutes to think about it. And can anyone think of an idea how to solve it? And what would be the complexity of that idea of yours? I mean, can you do it efficiently in some sense? So I'm making life easy, because if you want to use FFT, for example, with binary, things are always easier. We saw that we didn't need the Abramson-Kosaraju idea in order to count mismatches in a binary alphabet. That was done in time O of n log m without a problem. So the question here is, what happens if the alphabet is binary? And this is what I want to find out. How? In other words, I want to find out all the places in T that are different from. We have a text T. Okay, so our problem is input text T over 0, 1, pattern P over 0, 1. Find all text locations where all text locations J, where Tj is not equal to P1, Tj plus 1 is not equal to P2, and Tj plus m minus 1 is not equal to Pm. So that's our problem. And the question is, how can you do it fast? So there's a pretty simple and amazing solution here that says, consider P complement, and then do exact matching. So because the alphabet is a binary alphabet, if you look at the complement, every place where you find the complement is exactly the place that you want. And that is done in time. So the time is linear, is O of n. So here we are. We have a relation that is not transitive, and yet we have a linear time algorithm. But because the alphabet it's a very particular situation. The alphabet is binary. Okay, so now same question, alphabet not binary. So over sigma. It could be finite, or it could be even infinite. I don't care. Let's assume finite, okay? Start with finite sigma. Now the trick of saying look at the complement doesn't work because there is no complement. In fact, all the complements is an exponential number. Already, if your alphabet is 3 elements, then if you want to generate all the strings that are not the one that you're looking for, and let's say use the Korek algorithm. So Korek says you can find a bunch of strings in time O of n log m, right? So take, so the alphabet is, let's say, 3 elements. So generate all the strings that are different from P and find them according to Korek. So the problem is that there is a m to the m, there is 2 to the m options to consider, because in every location there are, even for a trinary alphabet, in every location it's either this or that. So it's 2 times 2 times 2 times 2 m times. So you have 2 to the m strings to consider. If you take these 2 to the m strings and build Korek, yes, your search time is going to be n log m. But your pre-processing time is going to be 2 to the m, which is exponential, and that's too much. So that's not the way we want to do it. So, okay, is there anything else we can do? Okay. So the suggestion now is, fine. It's like the tea and the coffee, right? This is how a computer scientist should think. What problem have we solved already? We know how to find the number of mismatches, both for a finite alphabet and for an infinite alphabet. For a finite alphabet, we know how to do it in time O of n log m. And for an infinite alphabet, we know how to do it in time O of n square root of m log n. So this is, we know how to count matches or count mismatches, whichever. We know how to do both. However, what does it mean that Tj is not equal to P1, Tj plus 1 is not equal to P2, and so on? It means that you have m mismatches or 0 matches. So do your algorithm that counts the number of matches, that computes the Hamming distance, and if the Hamming distance is is not m, then it's not a match. If the Hamming distance is m, then you have a match. So every location in the text where you have non-zero matches is not a good location. But if you have 0 matches, that's the location. And we know how to count matches. This is the time we have. So from the algorithms we have in our hand, we can do that. Okay, so this was an easy problem, but interesting in the sense that, all right, we have a relation, and this relation is not transitive. Sometimes we can even do it in linear time, and if we can't do it in linear time, we know how to use convolutions in order to solve it. Okay, so now let's look at another matching relation. So S match, it's called the less than relation. S matches T if and only if Si is less than or equal to Ti for all I. Now, this would be the following situation. Suppose what you have is so the text is some sort of a graph. So this is the text. And your pattern is also some sort of a graph. But you want to find all the places where when you shift it, the pattern actually matches under the text. It doesn't stick out. So this would not be a match because the pattern sticks out. This would be a match because the pattern doesn't stick out. And this is not going to be a match also because it sticks out. So you want to find all the places where the pattern fits in under the text. Now, so here is another one of these tricky situations. On the one hand, the less than or equal relation is transitive. If A is less than or equal to B and B is less than or equal to C, then A is less than or equal to C. However, transitivity is a necessary condition for the KMP algorithm to work. If you don't have transitivity, you can't do it. But it's not a sufficient condition because what you need is something even stronger than transitivity. In some sense, you need not just that if A is equal to B and B is, if A is less than or equal to B and B is less than or equal to C, then A is less than or equal to C. So this is the regular transitivity. But we need something else, that if A is less than or equal to B and C is less than or equal to B, we want to know what is the relationship between A and C. And we don't. In an equality, we know that. But here we don't. And what does that mean as far as we're concerned? It means that we may miss. Okay, so if we do KMP, anything that KMP finds is going to really be a match. But we may miss matches because suppose, for example, when you build your automaton, you say, okay, I get stuck. I want to build the automaton from 1 to I. So I want to find out what's the largest prefix here that's less than or equal to a suffix here. And that would be the next shift. However, when you're searching the text, it's true that that would be a shift, a good one. But when you're searching in the text and you're saying less than or equal, it could be that the text is also greater than or equal from here. The pattern is not, but the text is a lot bigger, so you could have shifted even once. So maybe your pattern was 5, 1, 2, 3, 4, 5, 6. Okay, so if you match it to the text and you're less than or equal to text, everything's good. The next shift that you can do in the pattern is this one, 5, 1, because the 5 is bigger. But if the text was actually 10, 11, 12, 13, 14, 15, 16, then your next shift would have been this one. And you don't have any way of knowing it from the pattern. So the problem that you have here is that, yes, if you do a witness table algorithm or a KMP and you find a location, then that location is a true location. But you may miss locations. And why is that? Again, because this is less than or equal to that, and also this is less than or equal to that, but I don't know the relationship between each other unless I have the text itself. And in the equivalence relations that we had before, that was fine because because any relation between any two of them is going to force the same relation on the third. Okay, so here we have the less than or equal. I hope that the relation is clear. And we want to find an algorithm for it. So again, let's assume, let's make life easy. Let's start with assuming that I don't know what the text alphabet is. It could actually even be infinite. I don't care. But let's assume that the pattern alphabet is fixed. So it's, let's say, C1, C2, C3, C4, up to CK. And that's fixed. So our patterns are going to be strings over this alphabet, C1 through CK. These are numbers, not these alphabets. CI are numbers. And our text is going to be any number. And we want to find all the locations where the pattern is less than or equal to the text. So how do we do that? Afterwards, I'm going to move on to the general case. But right now, let's start. The pattern has a fixed alphabet. I can steal one, right? Any ideas? Yeah. I don't want to. We don't need to get into the mechanics of FFT. The idea is right. We want to use the FFT, but you don't need to change to get into the how it's done. You can use it as a black box. So remember that the FFT, the powerful thing that has helped us so far is that when you have a, let's say, a binary string and another binary string, you can count for every shift the number of clashes of ones and ones. That's something that you can do in time n log m. So use that, and what you need to do is see how I can reduce my problem to a finite number of such counting clashes between ones. So that would be the trick in a lot of these problems, is how do you reduce your particular problem to a finite number of counting clashes of ones. Okay, let's do it this way, okay? So make it easy on yourself. Assume that sigma is actually only C. It's one letter. And you want to find, well, one letter is not good, but two. Okay, so sigma is 2. C1 and C2. And you want to find all the places where there is a less than or equal match. Okay, so suppose that you take your pattern, and every place where there is a C1, you put a 1, and every place where there is a C2, you put a 0. Okay, so now you have all the ones in C1. Now, what would be the locations in the text that would be good? Are all the ones where the number in the text is greater than or equal to C1, right? That would be a good text. So suppose that you now go through the text, and all the numbers that are less than C1, you make them ones, and all the other numbers you make zeros. And every place in the pattern where there is a C1, you make a 1, and every place else you put a 0. Now when you multiply, what do the clashes mean? What does 1 times 1 mean? Okay, so chi chi of less than C1 of the text is going to be 1 if the text, let's see, text I is going to be 1 if Ti is less than C1, and 0 otherwise. And chi of C1 of the pattern is the way that we defined it, okay? So everywhere where there's a C1 in the pattern, we put a 1, and every other place we put a 0. So chi C1P times chi less than or equal to C1T, what would that give us? All the clashes of what? What would it count? For every location, what does it count? The number of times that there is a C1 in the pattern, and in the text, there's something that's less than C1. Right? Okay, everyone agrees? So let's look at an example. So suppose that C1 is equal to C1 is equal to 5, C2 is equal to 7. Okay, and the text is 1, 2, 10, 5, 3, 4, 6, 5, 10. And the pattern is 5, 5. And the pattern is 5, 5, 7. So we want to find all the locations where the pattern is smaller than the text. Okay, first of all, let's see if we can figure it out here. So, in fact, here, this is one of them. 5, 5, 7 is smaller. And here it's smaller, 5, 5, 7, and also here, 5, 5, 7. All these locations are going to be matches. So what are we going to do? So the first thing we do is we want to find out all the locations where the 5s are okay, where the 5s are less than what's in the text. The way we do it is we consider chi 5 of p, which is equal to 1, 1, 0. And in the text, we look at chi less than 5. So the text is going to be 1, 1, 0, 0, 1, 1, 0, 0, 0, 0, 0. That's going to be the text. Because these ones are all the locations where the number in the text is less than the number in the pattern. Every time that I put the pattern under the text in these locations, we're going to have a clash of 1 and 1. A clash of 1 and 1 means something in the text that's less than the guy in the pattern that's supposed to be next to it. So let's see where we're going to be in trouble. So 1, 1, 0, if we put them here, we have 2. So there's going to be 2 clashes here. And here, 1, 0, 0, there's going to be 1 clash. Here there's no clash. And 1, 1, 0, there's no clash. And 1, 1, 0, so here there's no clash. 1, 1, 0 gives us 1 clash. 1, 1, 0 is 2 clashes. 1, 1, 0 is 1 clash. 1, 1, 0 is no clash. All of these are no clashes. So that's the result of the multiplication that we're going to get. But look at what this means. Why do I get a 2 here? Because when we try to put 5, 5, 7 under this 5 has a problem and this 5 has a problem. The text that's adjacent to this 5, the text that's the appropriate text element is less than it. So it's 1 times 1, it gave us a 1. And then here also it's less than 5, so that gave us a 1. You add the two of them together, you get a 2. That's what the FFT does. So what you get here is actually the number of elements in the text in that particular position that are in fact smaller than the pattern. So it would be tantamount to counting the mismatches. But we're not done, because we would think that this is also a good position, since here we have a 0. Everywhere you have a 0, the 5 is good. So we would think that this is a good place because we have a 0. And indeed, if you put a 5, 5 here, the 5 and the 5 are good. It's the 7 that gives you a problem. But we haven't done the 7 yet. So we're going to do another convolution for the 7. So we do the same thing. We look at chi 7p, and that is going to be 0, 0, 1. And then the text is going to be anything that is less than 7. So the text is going to be 1, 1, 0, 1, 1, 1, 1, 1, 0, 0, 0. So that's the text. So those are the things that are less than 7. And now if we multiply the pattern by the text, it's 0, 0, 1. So here we have a 0, because in fact the 7 does not contribute an error here. So here we have a 0. 0, 0, 1. Here we contribute a 1. 0, 0, 1. It's another 1. 0, 0, 1 is 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 0. 0, 0, 1 is 0. All of these are zeros. So our two solutions are this array and this array. This is the number of clashes we had between 7s and numbers that are smaller than 7. This is the number of clashes we had between 5s and numbers that are smaller than 5. If we add them all up, if we add both of them, what we get is the total number of clashes. So here we have 2, and here we have 2, here we have 1, here we have 2, here we have 3, 2, 0, 1, 0, 0, 0, 0. Okay, so the number of errors that we get for all the first ones are here. That's the total number of errors. And from here on, all of them are 0, because in fact we saw that we have a match of the pattern under the text. Now, in general, when we have C1 through CK, then what are you going to do? Your algorithm is going to be so the algorithm will be for I goes from 1 to K. We do the following. V I is chi of CIP times chi of less than CIT, and do. Then V is the sum of the VI, the sum over I, and then every location in V that is 0 is a match. Time O of K times n log m, which since K is fixed, it's O of n log m. Question about this? Everything clear? All right. So now you know exactly what's the next thing I'm going to ask you. unbounded alphabet. Now, let me caution you. So you obviously are going to have to think now about some idea like the Abramson-Kosorajo idea, something about using the FFT for blocks and then fixing things within blocks. But here, there's going to be a bit of a difficulty because for the match, remember that what we did for the numbers that appeared a small amount of time in the pattern, what we did was we said in the text, okay, let's see. I am the number that appears a small number of times, right? We were counting matches. So the text says, since I am this number, the number only appears 2 times. So let's add to the two bins that these numbers would match. But here, if we're talking about greater than or equal, what does it mean for a number to appear a small number of times? If a text is big enough, then all the numbers are there. What is he going to say? I'm a huge text. Everybody matches me. So what am I counting? So he's going to need to count all of them, and that's already NM. And NM is what we don't want. So there's actually another trick that is needed for this that we haven't seen because we didn't need it in the last time we used it, but now we need this trick. So I'm going to show it to you. Now I'll go back to the make this big. Okay. Yeah. Here we are. Okay. Now, life would be a lot easier, and we'll see why in a minute, if the text is not going to be huge. So let's, oh wait, it's not, you can't see anything. Here I am happily going on, but no one can see a thing. Okay, so let's assume that the length of the text is no more than twice the length of the pattern. Now, you're going to say, well, what kind of assumption are you making? It's like saying the pattern is huge. It's like half the text. So if the text is less than or equal to 2 times m, it means that the pattern is at least half the text. Isn't that a terrific assumption? I mean, as someone says, what does assume mean if you look at the way it's written? It's like when you assume, you make an ass of you and me. So what are we assuming here? So whenever we make such an assumption, we need to prove why we can do it. And the point is that even though the text length is no more than twice the pattern length, we can assume that, and still, if we can find an appropriate algorithm for this, we'll find an appropriate algorithm for huge texts. Why? So here is a claim. Let's say that we can do some sort of a pattern matching. I mean, This one, this was written for pattern matching with mismatches, but it doesn't matter. Any pattern matching algorithm that we can do. Assume that we can solve it in time O of m times fm for texts of length at most 2 times m. Okay, so be it m times log m, so fm may be log m, it may be square root of m log m, it may be m to the third. I mean, I don't care what it is. So it's m times some function, and that is the time that it takes me to do the pattern matching over small texts that are at most twice the length of the pattern. Then what I'm saying is that I can, in general, solve in time n times fm for general texts, no matter how big they are. And so it means that if, for example, I'm going to show you how to do the less than matching on small texts in time m times square root of m log m, then I'll be able to, then I can immediately know that no matter how big the text that you give me, I can solve it in time n times square root of m log m, even for big texts. So this is what this claim is saying. And what it's saying is that that assumption that we made, that seems like such a preposterous assumption, is really a tame little assumption to make, because it really doesn't do any harm. It just helps. So we need to prove this claim in order not to say that the claim is preposterous. Yes, yes, yes. Of course. But the claim is true no matter what. But in our case, because n times m we know how to do, then, however, suppose that your problem was such that you cannot even in n times m find it. And there are matching problems that are even NP hard. So it could have been something that the time to do it is m to the fifth. So it's m times m to the fourth. So you could get n times m to the fourth. That's the idea. Okay, and how do we prove it? So you have a very long text. Split the long text into pieces of size 2m. Now, your pattern is of size m. So in time O of m times fm, check the pattern occurrence in each of these substrings. So where are the occurrences of the pattern here? Where are the occurrences of the pattern here? Where are the occurrences here? So for each one of these substrings, we're going to spend O of m times fm time to check the matching. Okay, so far, how much time have we spent? We have n divided by 2m pieces, and for each one of them, we spent m fm time, and so you get rid of the m, and you get O of n fm. Okay, so the idea is, I don't care what's happening in the other ones. I only care what's happening in my little corner of the world. So do that. However, and here is where you're going to jump up and down and say, hey, what do you think that we are? What about, so you find all the matches here, but then if something is straddling 2 of these, then you're not going to find it. So you're not finding all the matches. I say, okay, well, let's also cut the text into pieces of 2m, but with an offset of m. So these are the green boxes. So this is a piece of 2m, this is a piece of 2m. And also do mfm time in each one of these pieces. So how much time are we doing? So we have n over 2fm for the top, and n over 2fm, I mean, for the black substrings, n over 2fm work for the green substrings. So together, we have nfm work for all substrings. And at this point, we found everything, because every string every occurrence of the pattern is going to be either in a black one or in a green one. If it's already past this green one, then it's going to have to be in the next black one. So you found all of them. Okay, so see? It doesn't really matter. Let's now look at small texts. We don't need huge texts. What difference does it make that there's a huge text? The fact that that at the end of days something is happening has nothing to do with me now. If a tiger can live together with a lamb at the end of days, does it have any effect on me in my life? No. Okay, so so this is the this is the proof. Of course, you need to take care of the indices. So if P matches T in location I for I mod 2M so and so, so there's actually the way that you compute the original index according to what you find. But it doesn't matter, okay? I mean, we would know how to do it. Find out what block you're in, multiply it by, if you're in the ith block, multiply it by I minus 1 times 2m, and add whatever you have, and you're there. So here's the time. So therefore, the problem that we're considering now is we have a text, T0 to T2m. That's all. And we have a pattern, T0 to PM. And what we need to do is find out all the places. Well, okay, here it says the number of mismatches, but this was an earlier version of the Abramson-Kosaraju paper that was more complex, but that it wasn't necessary for the mismatches. So what I showed you was actually a later, much simplified version. Like I told you, it's when you look at a problem and you understand what's happening, everything simplifies. In the original papers, they actually did need this division, which we didn't. But we do need this division for the less than or equal matching. And so our problem is we have T0 to T of 2m and P0 to P of m. And for every text location, we want to find out the number of mismatches, meaning the number of times that the text is going to be less than the pattern, resulting from trying to match P0 PM to TI plus M. But match here means less than matching. Okay, so now that we have that, we're now going to be able to go back to our idea, but now there's something very interesting, because when we're saying that now when we're saying that a number is a frequent number, and we said that it occurs square root of m times, well, square root of m times is both in the text and in the pattern, because the text is also 2m. So altogether, the text and the pattern are 3m. So now our frequent numbers, and this gives us a lot of leeway, a lot of options to play with, because if our frequent numbers are the ones that appear both in the text and in the pattern a lot of times, then we can use the FFT in order to do our counting for these guys, and what's left are numbers that even in the text don't appear a lot of times, let alone in the pattern. So at that point, maybe we'll be able to work it out, because we're not going to say, well, that the text matches a lot of people, because if it does, then it's a frequent number, and then it wouldn't match them. So let's see how we're going to do this. So the algorithm outline is going to be the following. We're going to reduce the alphabet size to O of square root of m. And if we reduce the alphabet size to O of square root of m, so the FFT can already do the work, because we saw that, okay? I mean, when we said C1 through CK, and we said that we can do it in k times n log m, all right? So if the alphabet size is square root of m, then in time O of square root of m log m, square root of m times m log m, we'll be able to find all the locations where the alphabet is smaller than the other. So in the reduced alphabet, we're going to be able to count all these mismatches, all the places where the text is less than the pattern, in times square root of m times m log m. Once we do that, what's left is just to adjust to the original alphabet. And the adjustment is going to be what is going to take us the time, m times square root of m. Now, again, I said here square root of m, and the time is going to be square root of m times m log m. So we still, it's not the optimal, but it's easier to think of it this way. In reality, what you're going to do is reduce your alphabet size to square root of m log m. And at that point, everything is going to be the optimal. Okay, but let's right now do this simply, and even if we get n times square root of m log m, we know that afterwards to make it n times square root of m square root of log m is easy. We just need to make this alphabet size a bit bigger, and then everything else is going to be adjusted. All right, so how is that going to work? The total time is going to be this, okay? Okay, so how are we going to reduce the alphabet? For each one of the 3M symbols, because we now have 3M symbols in T and P, right? So we're going to construct a triplet that says, here is the symbol, am I in the text or in the pattern? And what is the index that I am in? Because at this point, we're now considering both the symbols in the text and the symbols in the pattern for our overall counts. So, so let's indicate if the symbol is in the text or in the pattern, and what is its and what is its index. And then we'll be able to sort the triplets by the symbol. So, or in our case, it's by the number. But in this example, these are going to be the sorted triplets, because if the text would be AACB, AAA, and then DADC, so consider these as some sort of numbers. So A would be in the text and in index 0. A is in the text and in index 1. There's also an A in the text and index 4, A in the text index 5, A in the text index 6, and A in the pattern in index 1. And then after the A's, we get the B's. B is in the text in index 3, and that's the only B we have. And we have a C in the pattern. No, we have a C in the text in index 2, and C in the pattern in index 3. And then we have the couple of these in the pattern. So this is how we're going to sort the things. You sort it by the symbol, then by the text or pattern, and then by the index. So, but it can be a radix sort, it can be any. So start by sorting by the symbol, then. Okay. Now, any symbol that has more than square root of m triples is going to be called the frequent symbol. So these are going to be taken out. Because like we said, the frequent ones, we know how to count their mismatches by doing FFTs. So that's what we did before. So we're going to move out all these frequent ones, and what's left are only these guys that appear less than square root of m times. All the triples that appear less than square root of m times. So, of course, the maximum number of different frequent symbols is 3 times square root of m, so that's wonderful. Now, for the triples that are non-frequent, now what we're going to do is the following thing. So what do we have? We have a bunch of numbers, n1, n2, up to whatever, but each one of them up to n L each one of them appears a small number of times, less than square root of m number of times. Maybe some of them only occur once, both in the text and in the pattern, because at this point, all the numbers are thrown in together. So let's actually, what we should do is actually the following thing. Let's split them into groups of size square root of m. And each of these groups is going to get a representative. So we'll take the representative for each one of these groups and now run through and construct a text in the pattern that is, well, not run through and construct a text in the pattern, but when we have these representatives, let's take out all the frequent numbers out of the text and out of the pattern, so what's left is only the non-frequent ones. So what it means is that if I'm in the text, the number that I have is going to be a non-frequent number, because if the number I had was frequent, I already took care of it. So I have a non-frequent number. If it's a non-frequent number, then all I have to do is check out where I am relative to the numbers in my group. So, and that means that I only need to check out square root of m numbers and not m numbers. So let's see how we're going to do this. Okay, so what did we say? Any symbol that has more than square root of m triples is called frequent, and all the frequent symbols, the triples of frequent symbols are going to be moved to the end of the list. Fine. The maximum number of different frequent symbols is going to be 3 times square root of m. Yes, we said that. The triples of non-frequent symbols, we're going to split them. A group is square root of m consecutive triplets, and we extend it until the change. So we want basically to have we don't want the same number to appear in two groups. So if we have the numbers, 5, 6, 7, 8, 8, 8, 10, and if square root of m is going to split it here, then I don't want the 8 to be in this group and in that group. So I'm going to extend the group all the way to here, and it's still going to be no longer than 2 times square root of m, because none of these numbers appear more than square root of m times. Now, this actually is the way that they work in Disneyland, for example. Because in Disneyland, if you're standing on line, and that is the main attraction in Disneyland, actually, is the standing on line. My kids, when they were little, I used to take them to Disneyland. And after twice and 3 times, I got so disgusted with the entire thing that I would come in and set my watch on a stopper, and every time we got on a ride, I would run it, and when we got off, I would stop it. And then at the end of the day, after you spent 14 hours sweating and standing in line, I showed them, do you know that after this 14-hour days, we were only 7 minutes and 53 seconds on actual rides? And so after this, they said, don't come with us anymore to Disneyland. They just went with their mother, because I would dampen their excitement by the fact that I said after this 14-hour day, all you did was 9 minutes of actual fun. So, but the way they do it there is you stand on line to go to some attraction. So you stand on line, and they count. Okay, that's it. Up until here, you guys stay there for the next cycle. But if there's a mother that says, wait a minute, 2 of my kids are there here and 2 of the kids are there, what are you saying? So they'll say, okay, you 2 also go in. So this is how we're doing it. Like the lines in Disneyland, if we're looking for these sorted numbers, and if the same number actually extends, so we put it in the next group. So now what we have is groups of numbers. And these groups of numbers are are going to be of size no more than square root of m. Okay. Now we're ready for the algorithm itself. So yeah, this is an explanation of how we do this Disneyland thing. Now for every group, we're going to take the symbol in the leftmost element of the group as the group representative. So obviously, the number of representatives we have is O of square root of m. So here is an example of this. Now we construct the text and the pattern by just putting the group representatives. Now, again, the frequent items are their own sets, and they represent themselves. And in fact, here it says put them in the end, but you don't put them in the end. You put them between the groups that they're supposed to be, because we're sorting things and we want less than or equal. So you sort them, you put the representatives of the frequent items in their location. And now altogether, between the frequent items and the group representatives, you really have an alphabet of size square root of m. In an alphabet of size square root of m, you can of course find the less than matching in time m times square root of m log m, because that's the alphabet. So you multiply it by every element of the alphabet and you found it. And now what we have is actually, so after we do all this, what do we have? So here is the text. We have, for every location in the text, we have the number of text elements that are less than the pattern elements. So that's what we have now. But as far as the representatives are concerned, so it could be, I mean, any place where you have a non-zero number is clearly not a place that you have an occurrence that you want, because what it means is that you have in the pattern an element that is in one group, and the element in the text that's there was actually in a group that is smaller than my group. So obviously that's a problem. So any location here at the end of this stage of operations, any element here that is non-zero is clearly already bad. The problem is that some of the elements that are zero are still bad. Why? Because what does it mean? It means that all the text, so it means that here I have the pattern and the text here, and in all the text elements that are by the pattern element, they were all in the same group, or they were in a bigger group. In a bigger group, it's fine, but they could be in the same group, and I counted this as okay because they're in the same group, so it's less than or equal. So I counted as okay, but it's not really okay because it could be that they're in the same group, but this one was 8 and this one was 7, and then although they're in the same group, it's a problem. Okay? So the only remaining problem is what happens within a group. So I counted already all the mismatches of elements in different groups. But elements within a group, I may have a problem with. But at this point, you can already visualize how you're going to solve it. So at this point, when you're come to a text element, ask yourself, first of all, am I frequent? If I'm frequent, forget it. And if I'm not frequent, let's see what group I'm in. And now, go through the square root of m elements in my group, and anybody who is bigger than me, add the mismatch. So now every text, in fact, does square root of m amount of work. So we have the O of m O of square root of m times m log m for the groups, and then O of m square root of m to adjust within the groups. And at this point, we're done. So now we know how to do the mismatches in time O of m square root of m log m for small texts. And because of the claim, it means that even for long texts, we know how to do it in time O of n times square root of m log m. Yeah. Because every group is at least root m in size. So there's m elements, and every group is of size root m, between root m and 2 root m. So you have square root of m groups. Now, in reality, what you're going to do is the frequent element should be not square root of m, but square root of m log n. But that's an adjustment at the end. Okay, so the key observation here is that every mismatch counted in t time in p prime is also a mismatch in t and p. Because if my group representative is in the pattern is bigger than the group representative in the text, then obviously my element in the pattern is greater than the element in the text. So that's for sure. But what we needed to do is to adjust, and the adjustment is done by the idea that we said, that you stay in one place, you look at the square root of m elements within your group. So here we are in the text. I look at the square root of m elements in my group, and any of them that's in the pattern and is bigger than me, I put in a error, a mismatch. So that ends this, and the total algorithm time is O of m times square root of m log m. And as we said, we can adjust this. We can adjust this to be square root of m square root of log m. Okay, so much for the less than matching. So is this clear? So let's see one more example. And that's the example that I showed you yesterday with the beautiful biology slide. Okay. Yeah. Okay, so the biology slide you saw, and they do have beautiful slides. And now let's see the problem. So what are weighted sequences? When you, the original genome project, the famous paper that was published by Celera Genomics after a couple of decades of work in which billions of dollars were extended, and the human genome was sequenced, finally. Whose genome was it? They're saying human genome. I mean, whose genome was it? We obviously don't have the same genome, otherwise we would all look the same. So we don't have the same genome. So whose genome was it? So it turns out that, yes, we do have different genomes, but the differences are not that much. And in the 10 to the 9th long genome, there are only a 30,000 or 40,000 locations where we differ. Now, even 40,000 locations that we differ is enough to make a difference, because 2 to the 40 is a huge number. So that's the number of different variations that we have. But all I can say is that after 2 to the 40 people are born in the world, we're going to start repeating. So there's got to be repetitions at that point. So uh, so we have what to look forward to. There's going to be copies of us in the far, far, far future running around. However, also something else, another sobering thought, is that if you today for a few $1,000s, you can get your own genome on a memory stick. So you pay a few $1,000s and they get your genome. So we paid billions and billions and billions for the first one, and now you go a few thousand, you get your own. And that's really specifically your genome. But when it comes to doing research, then what you want to do is find out what generally the genome looks like, because that can tell you something. So for example, there are probably a bunch of locations out of those 30, 40,000 where all of you are the same, but I am different. And I would be the same as all the other people in my neighborhood, but you'll be different. So because there are groups where this particular gene is prevalent. And it's also important because when people look at genetic diseases, then that's important. For example, in Israel, because there are Jews who came from all over the world, there are some connections, there are some groupings that actually can lead to some pretty bad diseases. Because if they both have the same kind of gene, then, and it's not a dominant gene, so there's some gene that if you get it from both father and mother, you're going to get a disease that you die before you're 5 years old, and there are such diseases. But if only the father has it, or only the mother has it, nothing. You're going to live a normal life. You'll just carry on the gene. So what they do in Israel is they make people who want to marry, they don't make, but they encourage, and a lot of people do that, to actually go and test their genes for these specific variations, to know that if two people are getting married and they know that there's a 50-50 chance, so half of their kids are going to die before they're 5 years old because of a horrible disease, they should know that, and they want to know that. So they can then figure out if they want to get married or if they want to have children and how to monitor things and things like that. So people do these things. But when you study all these genes, then you're saying, okay, my text is going to be the genome, and these are, let's say, the bases, and let's say this is a protein or whatever, and these are the bases. So you have a fixed number, 4 or 15 or 20 of possibilities. But what I want to know is what is the probability of seeing A1, what's the probability of seeing A2, what's the probability of seeing AK. So we want to say, here I have the genome, or here I have this string, and I'm getting it from a whole number, for a lot of different number of sources, and I want to know how many of those sources actually have A1 in this location, and how many have A2, how many have A3, and this is called weighted sequences. Now, in biology, they actually draw this thing pictorially very pretty, because they do it with different size letters. So, for example, if everybody has an A, then they're going to draw a big A. Then if it's equal, they're going to have like B, C, A, B, C, D for location 2. And then maybe location 3 is going to be a tiny A and a big B and a tiny C and a tiny D. So they draw it that way, and pictorially you look at it and you say, okay, I have a feeling of what is more prevalent and what isn't. But in our case, since we don't draw beautiful pictures like biologists, So what we're saying is, okay, yeah, you have, here is your string, and here's your index, and that's the probability of AI. Okay, so, and obviously, since these are probabilities, then the sum of these things is equal to 1. Now, so this text of probabilities, that is called the weighted sequence, because it's a sequence, but it's weighted. So our problem now is given a weighted sequence T, and given a pattern S1 through Sm, and given probability alpha. So we have a pattern. The pattern is a particular gene, and we're given a probability. So we want to know all the text locations such that P, this gene, occurs with probability greater than alpha. So we want to know that this particular subsequence occurs with a high enough probability in this group of people or something. So that's what we're looking for. So so in short, let's look at this example. So suppose we have A, B, C, D, and these are the probabilities in each one of the cases. And if alpha here is what was alpha? Well, I don't think I gave an alpha, but if you look at the second location, and if you look for what's the probability that ACDB appears there, so it appears in location 2 with probability 1, in index 2. In index 3, it appears with probability half, so it's already half. Then you multiply that by a quarter, because the D appears with a probability a quarter in this index, and then the B appears with probability 2/3. So the probability of seeing ACDB starting at location 2 is 1/12. Now, Kostas Iliopoulos and his group did a lot of work on these things, and they answered a number of questions. One of the questions was they wanted to do exact matching. In other words, what is exact matching? I'm giving you a pattern, and I'm giving you a probability, and I want to know all the places in the weighted sequence where that pattern appears with that probability. So that's the exact matching in their context. So clearly you can't do a KMP here, but what we'll see is that this can be done with FFT. In fact, I will let you think about it a bit. Then the second thing they did is they constructed a weighted suffix tree for indexing. We didn't talk about indexing yet, so we're not going to talk about this. But think a moment about how you would want to do, how you would use FFT in order to do an exact matching of your pattern. So you get a text, you have a pattern, and you have a probability, and you want to find out all the places where the pattern matches with that probability. Can you use FFT for that? Now, at this point, obviously what you need to think about is not, here think not about the usual one clashes with one that I said, but think about what general FFT actually does. A general FFT takes a pattern of numbers, takes a text, it shifts the pattern on the text, and in fact what it does is a dot product at every location. So it multiplies all the numbers one by one and adds them up. Multiplies all the number one by one and adds them up. So that is the so that's what an FFT does. Now, in some sense, here we have a bit of a problem, because we are, in order to get the probability, what we actually do is multiply the probabilities. And the FFT doesn't multiply things. It actually adds them. However, what is the natural way you would do in order to convert multiplication to addition? Take the log. So change your probabilities from probabilities to log probabilities. At this point, what you want to do is add them all up and see that the addition of these things is less than or equal to the log of the probability that you're looking for. And at this point, you got it all. So you convert the probabilities to logarithms. So now you're using sums instead of products. And now look at every text row separately. So you have 4 rows, you have 20 rows, whatever number of rows, it's constant. So you consider every row separately. So let TA be the text row of A. Look for just that. So fix the A. Now, the log probability of the pattern at every location is given by this formula. Because take the text row, multiply it by chi A of the pattern, reverse. So at that point, what you're doing is you are adding all the log probabilities of that particular letter. Now, because addition is distributive and commutative and all of that, so it doesn't really matter the order that we do this thing, right? So add all the log probabilities of A, add all the log probabilities of B, add all the log probabilities of C, and then add them all up together. So your time is going to be the number, you do a bunch of FFTs times your alphabet. And then you got it. So that answers the weighted matching problem. Okay, so here's an example. So if P is equal to AB, CAB, then you're taking the 1, 0, 1, 0, 0, 1, 0, you multiply it by TA, and that gives you the sum of the log probabilities of the A's. You multiply then the B's, it gives you the sum of the log probabilities of B, and then the C's, add them all up, and the time is O of n log m. Here you are, FFT solved this problem. So the FFT is like a huge, very powerful tool in a lot of these things. The biologists didn't even know about its existence. When they saw it, their eyes lit up. Okay. So what we can do now is look for what's called the weighted Hamming distance. So this is a problem that we looked at 2006, again with Iliopoulos, and Oren Kapach at that time was one of my PhD students. So, okay, so it's easy to do the exact matching, okay? But what happens if what you want to do is look at the Hamming distance of a weighted sequence? In other words, how many mistakes do I have in order, what's the minimum number of mistakes that I can afford, that I can allow myself until I can actually and reach the required probability. So that would be the weighted Hamming distance. So Hamming distance is the number of errors, but here we're not looking at the number of errors for matching here, but the number of changes I need to make in order to actually arrive at the required probability. But here, and this is beautiful because it's not symmetric. The mismatches are not symmetric. When you're saying that the errors that you have are in the text, or that the errors that you have are in the pattern, it's not the same thing. And here's why. So let's look at this example. Okay, so the question of the symmetry of the Hamming distance is clear here to everyone? Should I say it again? When you're looking at the Hamming distance and you're saying, I have a text, I have a text, I have a pattern. And when I'm asking you, what's the number of mismatches that I have in this location? What does it mean, the number of mismatches? Do you care about whether mismatches mean there were some errors? Okay, so the reason it doesn't match is because somehow there's an error. But do you care if the error was in the text, that someone actually input the text wrong but the pattern is correct? Or do you care if the text is 100% but the person who wrote the pattern mistyped or got it wrong? You don't care, because an error here or an error here means the same thing, and the number of errors is the same whether they were in the text or in the pattern. So that's what symmetry means. But here in the weighted sequences, we get to see an example of a relation where if the errors are in the pattern, it means one thing, and if they're in the text, it means something else. And you may have a different result. And in fact, in one of the cases, you may have a result, and in the other one, you may not have a result at all. Because when you're saying that, let's find out what's the Hamming distance in some situation, then every location has a Hamming distance. At worst, when I am in some location and I'm saying everything is wrong, so the Hamming distance is m. But there's no such thing as a location not having a Hamming distance. Here what we're going to see is that there are locations where you cannot fix it. There's no amount of fixing that you can do. So Hamming distance m means that if I fixed m locations, I would have a match. Where am I fixing these m locations? I don't care. I fix it in the text, I fix it in the pattern. But here, you will see that if you fix m locations in the text, then you're fine. But if you fix m locations in the pattern, it doesn't matter. Even if you fix all the locations in the pattern, you're still not going to get a match. You can't fix it. And so it's not symmetric in that sense. And that's another reason why I'm bringing this example, is that you see that the world of pattern matching is not like that guy said, that you hear t is equal to t0 to tn, p is equal to p0 through pm, and then you fall asleep. And you wake up and it's all the same. No. These relations behave differently. And it's an amazing thing. So let's see the example here. So let's assume that the errors are in the text. In other words, when I put a pattern, I give you a pattern. My input is a pattern and a probability. Now, I want to find out all locations in the text that are where the pattern matches within this probability. Now, obviously, we know how to find all the locations where it matches. We saw that before. But now what we're saying is, for every location in the text, we want the Hamming distance. What does that mean? How many places in the text do I need to change in order to finally make the pattern match? Now, clearly, you can always make it match, because if you change the probabilities in the text to be 1 in a certain location, fix a location in the text, and change all the probabilities to be exactly 1 in the appropriate pattern location. So if the pattern wanted to see an A, give it probability 1. If it wanted to see a B, give it a probability 1. And at that point, the pattern is going to match the text with probability 1 by making all these m changes. And what we want is the minimum number of changes that we want to make. So here's the example. How many text elements have to be changed? So they will have probability 1, matching the corresponding pattern symbol, to produce a match at this location. So here's the example. We have that text. The pattern is ACDB, and the probability is 1/3. So that's the example we have. So we're saying that at location 2, this location, there is a match with 1 mismatch. Without a mismatch, there isn't a match, because as we saw, you have 1 times a half times a quarter times 2/3. It's 1/12, which is smaller than 1/3. So without making changes, you don't have a match. But if we're going to change this location in the text to be 0001, at this point, you have 1 times a half times 2/3, which is 1/3. So you'll have a match. So a single change is going to give you a match. And what we want is to find this single change. Now, if we assume that the errors are in the pattern, meaning how many pattern symbols need to be replaced in order to have a match at a given location, here we may not be able to fix it at all, because it could be that already we have the highest probability as it is. So no matter what you change the pattern to be, your probability is only going to be less. So in this particular case, if the pattern was A, B, C, D, and alpha is a third, like before, take location 2, there's no match that exists, even with 4 mismatches, because what are you going to change your pattern to be? A is already the highest probability that it is. C is the highest probability. If you change it, you can't increase that probability. D is also the highest probability. And B is the highest probability. So what are you going to change them to? Doesn't help. So here, there's not even any there's not even any solution. So we have an example here of a relation where the Hamming distance isn't symmetric. No, because we're counting the number of changes. If so so this gives you the minimum number of places that you need to change to 1 in order to match. Now, if you want to go back and say, okay, well, it will match even if I don't change it exactly to 1, but to less than 1, then you can do that. But you cannot, by changing in a different way, have less places that you change. So if you want to say, I want to minimize the number of places I change, then you may as well change it to 1, because any other way is going to have more places that you need to change, if anything. Yes. So that would be, that actually what you just said is a problem that I think is worth pursuing if the biologists think that it makes sense as far as they're concerned. From a theoretical point of view, it seems like a good problem. So there's no reason not to look at it. So you can say to yourself, okay, so you understand the point. The metric that was defined here is the Hamming distance is the minimum number of text locations that need to be changed. But what happens if that's not the kind of thing that I want? What if my measure is going to be not the minimum number of places that is changed, but rather minimize the number of so look at so what we basically have, I mean, I'm trying to define a reasonable problem, and that's a way to define it. So what we basically have is we have an array VA1, VA2 up to VAK. Okay, so let's assume that what we want to do is construct new arrays VA1 prime, VA2 prime, up to VAK prime, such that what you minimize is, let's say, the sum of the distances of the new arrays from the old arrays. And then you can even say, what do I mean? Am I in L0, L2, L1? I mean, there's an infinite number of problems that you can research here by this definition. But the definition would mean that let's minimize the distance of the arrays rather than the number of locations that I change. So it's certainly a reasonable theoretical problem to look at. I don't see any obvious way of solving it. It needs a bit of thinking. It may be, I don't think it's trivial, but it may be doable. The reason that I am doable, I mean, I'm not sure that you will be able to get something like n log m for something like this. In fact, I doubt it, because to look for, because what you're saying is now that you want to find arrays, you want to find some metric of an array that moves all along, and then even to add them and minimize them. It could be, for some metrics, even if the length of the pattern is exactly the length of the text, that would be NP hard, as we know. So, and if it's not NP hard, then the question is, can the shift be somehow utilized? I don't know. So it would really depend on what metric do you use for the distance between the arrays. In general, it does not look, it's not a trivial problem. I don't think it's an easy problem either, but it could be that for some metrics, there would be a solution that is not NP hard and that is reasonable. So yes. Okay, so in fact, I'm very happy because these kinds of questions already halfway through the course, and we're getting questions that can generate new research problems. So that means that the level of knowledge here is increasing in the area. So that's good. I mean, you're not going to end up the course and say, "What did I learn?" I mean, you now have a well, at the end, for sure, you're going to have a basic knowledge that is certainly going to allow you to do work in this field. You'll need a lot of reading, of course, but yes, you can already conceptualize what's happening. Okay, so in that paper, we actually solved both types of these mismatches, and we looked at all kinds of flavors of edit distance, which we haven't spoken about here because all we spoke about is Hamming distance, which is mismatch. We are going to talk about edit distance a little bit later on, especially since, I mean, you may have seen the edit distance in some courses because it's a dynamic programming example. It's a good example for dynamic programming. But there's, we're going to see some nice algorithms to do that faster, that dynamic programming, using some techniques that we'll see later on. But in the paper, there are all kinds of works on a lot of flavors of the problem. But what we can see here is let's look at the simpler of the mismatch definitions. In other words, we're going to look at the locations to the text. And I am putting the problem here in a very simple form. Let's say that we have a text of natural numbers, a pattern of zeros and ones, and the natural number e. And what we want to find out is for every text location, the smallest number of text locations that when changed to 0, bring the convolution result to be no greater than e. Okay, so I'm changing the negatives to positive, dropping the requirements that it's log probabilities, but basically if you know how to solve this, you know how to solve that. So, but combinatorially, this is a neater problem to look at. So the problem is, again, now it's a simple problem. Forget about the biology. Forget about all the motivation. Now we're down to good old combinatorics. So here we are. We have a text of natural numbers. We have a pattern of zeros and ones because we are now looking at a single row, as it were. So we have a pattern of zeros and ones, and we have some natural number, and we want to find out for every location what's the smallest number of text locations that if you change them to 0, then the convolution result is going to be e. The convolution result is the dot product. So So we have a bunch of numbers, 5, 10, 16, 11, 13, whatever. And then we have a pattern of zeros and ones. And so the convolution is we multiply them and we add and we get the result. So we take the dot product of the shifts. That's what the convolution does. So the dot product of the shifts may give you some number x that's greater than e. Now, obviously, if you change one of the, if you reduce these numbers to 0, this x is going to be lower, because even if something is facing a 1 in the pattern, you're facing a 1 in the pattern, but you became a 0 now. So that 0 is not going to be added in the sum. And so what we want to do is, for every text location, what's the smallest number that when we change it to 0, the convolution is going to be e. So that would be the number of mismatches in some sense. So you would say that for this location, if the text is changed to 0 at 2 locations, already I'm fine. I'm less than e. But if I change it at less than 2 locations, there's no way that I can be less than e. So it's a combinatorial description of what we were looking for before with probabilities. And how are we going to solve it? Again, we're going to solve it in the same method that we solved the less than matching. So you know already this picture. So we're going to say, okay, people, we're going to want to use Abramson-Kosaraju here. And because we are talking here about all kinds of numbers, so we don't want the n to be too large, so we're going to take a small m, split it into m over m, n over m subsequences of length at most 2m, and that's what we're going to do, and work on each one of them separately. Now, so here's the tower metaphor in some sense, because what are we going to do? Take all the text elements and sort them with the biggest at the bottom and the smallest at the top. So we have now all the text elements. And these blocks are of size square root of m. So the first thing we want to do is to find which block the sum is still less than or equal to e. Okay, so, all right, I jumped right into the solution, but think about it. The numbers that you want to change, because you want your Hamming distance to be the smallest, right? So what are the numbers that you want to change? The biggest. So the first number that you would want to change is the biggest number that faces a 1 in the pattern, because that is going to make the most difference. And then take the next biggest, and then take the next biggest. It makes sense, because why change small numbers? You're going to need to change a lot of them in order to reduce your total sum. So start from the big numbers. So you put the big numbers at the end, and you're saying, let's see how many small numbers can I add from the beginning until I finally get stuck, and I will drop all the rest. And in order to do that, so we sort them this way, and we say, okay, but we have the blocks, so it's easy to deal with the blocks. Let's, by FFTs, we always know that. So let's actually find the block where the sum is still less than or equal to e. So up until here, all these numbers, all these blocks, the sum is still less than or equal to e. We're still going to be happy. From here on, for sure, it's not going to be equal to e. So we have one block, that's the seam block, where somewhere in the middle is where we want to make the change. So it could be that we can add 1 more, 2 more, 3 more, but once we add the 4th one, we are in trouble. So we can do that. But again, to add 1 more, 2 more, if all you're adding is square root of m, it means that for every location, you're working square root of m time. So tower metaphor works again. So we have the blocks. We're first going to find the block where the sum is still less than or equal to e. Then we want to find within the block where the change occurs. Now, obviously, we're going to need to know for each text location how many text elements are in each block. So that's another thing we need to know, because that's what we're going to be doing here. And also because not every text location appears in every sum, since the pattern also has zeros. So if the biggest number in that particular, if the biggest number in the text in this location is a number that has a 0 in front of it in the pattern, then that number wasn't even playing. So we need to know that also in order to be able to to run our algorithm. So first of all, we want to know how many text elements there are in each block. Now, the text itself at this point, remember, the text is of size 2m. So if we sort all the text elements, we just have 2m text elements. And so the blocks that we divided was the thing that we did to begin with. So we sorted the real elements of the text, and we have these blocks. It's just that not all the block elements play a role in every location, because if there's a 0 in the pattern, then that block element doesn't play. So, but we do want to know, for every one of the square root of m block elements, how many elements from that block actually exist in my in this index. So how do we do that? Well, that you can do by a convolution. So you take, so every block, you take all the elements of the block in the text and you put a 1. Then you take the pattern and you multiply it. So the clashes of 1s against 1s are going to give you exactly the number of block elements that found themselves in front of a 1 in the pattern. So that's one convolution per block. So we do p times tj for every block j, and we save it in each text location. So every text location now saves square root of m information. Obviously, the time now is O of n times square root of m log m for the convolutions, and the information that you save is O of n times the square root of n. By the way, again, don't worry about this. At the end, it can be fixed to square root of log m. But it's just that to say, OK, the blocks are of sizes square root of m log m is hard to say. So it's easy for me to say square root of m. At the end, we're now all smart enough that we know that if we program this, we can actually change the block size, and then square root of m log m is going to work. OK. So now we want to know for every location how many blocks are still less than or equal to e. So at this point, we need to actually go block by block and see what is the number that it contributes to this e. So now we take tj to be equal to ti if it's in the jth block and 0 different. And at this point, for every block, we're going to do the multiplication. That is going to give us how much that block actually contributed. So we do it for every, so we do it for the first block, the second block, the third block, the fourth block. We do it for each one of the blocks. And for every location, we keep adding the results up until the number exceeds e. So at this point, again, we worked n times square root of m log m because we did square root of m convolutions. But we now know for every text location, what's the sum of the block values that are less than e. We also know how many such values exist. So all we need to now find out is within the block that we got stuck, what are the numbers that we can add? And that's what we do with the now with the other algorithm. So for every text location and every element in the seam block from the top to the bottom, if it matches a 1 in the pattern, you add until you exceed E. And again, because at this point you are within a block, so you go to the text, every position in the text. He knows what block he is in, and in that block, he's going to check against everyone. So we do that until the number exceeds E, and we're done. So the total amount of time for the correction is n square root of m, and we can fix it, as we said before, to actually be n times the square root of m log n. Okay, so in fact, it's very good. We're getting into a break point at this stage, and I think that I'm going to be done with the convolutions now and move on right after the break to the next topic. Okay. So we're going to talk about another concept now, and this concept is called deterministic sampling. Now, the concept of sampling is actually very practical and is in a lot of use in the sense of filtration. So a lot of searches nowadays, the way that they are done is you take a number of properties that are unique, and you search for locations where those unique properties occur. At that point, you assume that you end up with a very small number of options, and at that point, you're already going to start to do an exhaustive or naive algorithm, and it works out well because under the statistical assumption that what you're looking for is fairly rare. So for example, if you look at facial recognition, it's become very sophisticated and very successful recently. So much so that in Russia, the Facebook that they have there is not called Facebook, it's called VC, I think, and that's specifically Russian. So they actually have an app that if you walk around in the street and you see someone and you think you know that person or you want to know that person, I mean, you're a girl and you see a good-looking guy and you want to know him or something like that. So you take a picture and the app runs through the VC and finds that picture, and then it gets a name, and then it runs through all the database that exists, and maybe if that person puts his address somewhere, and so you can get all the information that's on the net about that person simply by walking in the street. You see someone, you click his photo, and the app is going to do the rest. So the reason they do it, now it's a scary thing, I think, and it means that our privacy is going to hell. But how do they do that? It's going to go to hell even more than that. I mean, in London, for example, the entire city is under closed-circuit TV. So everywhere you go, there's televisions in all the streets, presumably for safety and security. The thing is, there's so much, it's such a big city and so much television that you can't see everything, and no one is sitting there, no one can sit and monitor everything. But of course, if a day will come that things will be fast enough, then you can have every person, you have the face of every person. So you can actually have a big program that gets all the video feeds and sees who is everywhere, and writes down for every specific person where he is at any specific moment. So if anybody wants to know where you are, anybody being the government in this case, wants to know where you are, all they need to do is type your name, and it tells them right away, here you are, you're walking here. You can even see them in the video. So we're moving towards that. But how do they do that? They actually look at the face, and they look at specific points that are distinguishing of a certain face. And then when they run through all the faces, they just check these points, which is a very fast thing to do. And then they get a very small number of faces. And for those small number of faces, they do a faster check. So this is called filtering. You search for a specific small amount of information, which you can do fast. And then once you zoom in, you can afford to spend a little bit more time, because if you get only 100 faces that answer those particular that particular sample, then going through 100 faces is easy. Okay, so the point is that all this is statistics. And can we, Adobe really wants to update, right? It's constantly saying, I want to update, I want to update. Why are you closing me? So it's a statistical thing, and it says, okay, I'm looking for the sample, and I'm assuming that every sample actually does not occur a lot of times. What we're going to see now is an idea. It's a paper by Uzi Vishkin from, I think, 1991 or 2, and he called it deterministic sampling. The reason he called it deterministic sampling is he says, I can figure out a small sample that I can prove some very important facts about, and so I'm not bound by statistics anymore. You find this small sample, and provably you're going to be efficient, because whatever, not just what doesn't match the sample is not what you're looking for, but even the things that match the sample kill off a lot of unwanted information. Now, this can actually serve also very well for parallel algorithms, because if your sample is very small, you can in parallel search for the sample, and then once you find the sample, you can do your work, if you can prove that the sample is really far enough apart. And so his idea is, and that's why he called it deterministic sampling, he actually can prove that the samples give you locations that are far enough apart that now they don't overlap, and so you can check them in brute force and still be fast. Okay, so let's see what's the idea. The idea is you take the pattern and you find a small sample. So you take the pattern and you find these places, they're small, such that for all I, so we take an I in the text and we check the sample. If the sample positions don't match the text, that there's no occurrence of the pattern in the text. Now that's easy. That's any position that you pick in the pattern. If you go to the text and you go to that position, if it doesn't match, then there's no occurrence of the pattern. And in some sense, this is what the dueling algorithm used and said, okay, we're going to duel. If something doesn't match, then there's no occurrence, and that's the guy that I kill. However, what he wants to prove is more than that. So this is easy to satisfy. But what he wants to prove is the following trait. That if the sample positions match, okay, this is if they don't match. But if they do match, then you are guaranteed a very large area where the pattern cannot start. This is called the dead zone. So if I'm here and I look for these couple of sample points and they don't match, then obviously I'm not. But if they do match, then although I cannot kill me, but I have an entire dead zone, and I know no pattern starts in the dead zone. So that's the idea of deterministic sampling. And what we're going to do is how to find it. Okay. When I say large, or when he says large, the idea is that the size of the dead zone is m over c, where c is some constant. Now, if the size of the dead zone is m over c, let's say it's m, okay? Let's take c equals to 1, and let's say it's m. What it means is that if you find an index I that the sample matched, and the dead zone is of size m, it means that, in fact, any index that is there, if someone else is in that dead zone, you kill. And you yourself gets killed if there's someone else in the dead zone. So what it means is that you're left with, at most, one candidate for every m range in the text. If you only have one candidate for every substring in the text of length m, fine. Work on that one candidate, check if it's equal to the pattern, and if it's equal, yes, and if it's not equal, no. But what's your overall work? It's going to be n times m, it's going to be n divided by m over c times m, which is going to be n times c. It's a constant. It's linear. So here is the pattern matching algorithm that it gives. He says, for I goes from 1 to n minus m, here's what you do. You check the sample. If the sample is positive, then location I is set as a candidate. And then for every candidate, you kill all the candidates in its dead zone. For the remaining candidates, you verify in the naive way whether the pattern is there. So the time is going to be O of ns, where s is the size of the sample. Because for every text location, you have to check the sample. And then, for the verification, your time is going to be m times n divided by m over c, which is n times c. Since c is a constant, then your time is linear. So that's the Wishkin algorithm. 1990. Good thing it's 50. I was telling Neil before about memory problems that sometimes they got me in trouble. For example, this same person, Uzi Wishkin, when I was doing my sabbatical in the year 2000, I was in New York. And in the beginning of the sabbatical, Uzi Wishkin sent me some paper to review. And somehow I forgot all about it. And at the end of the sabbatical year, because I was doing the sabbatical in AT&T labs, the difference between a company like AT&T, if you work there, and a university is, in a university, if you have an account, that account is going to stay there forever. I still have accounts in Georgia Tech and at University of Maryland. No one is going to touch it. You had an account, your account is there. In a company, the moment, my contract ended at 5 o'clock in a specific date, at 5:01, my account was dead. I couldn't touch anything. That was it. So because in those days, in 2000, there wasn't any Gmail or anything. All the mail was there in the account. So the night before I finished, I went through my entire email to see if there's anything there that I need to quickly forward to my account in Israel, because I knew it was going to die. And then all of a sudden, I saw this email from about 10 months before that Wishkin sent me to review the paper that I forgot. And so I was panicked. I said, this is really, really not nice. But what am I going to do? I can't tell him, well, do you still need it? Because then you come out sounding really awful. So I said, I'm going to take the time. So I sat there, took an hour in that night, read the paper, wrote a review, sent it to him and said, look, I'm so sorry. I forgot about this until now, until I saw it. Here's the review. I hope that it's okay. So he says to me, well, thank you very much for the review. It's okay. It's not too late, especially because you actually had sent me a review about 9 months ago. But what I can see is that although you're senile, you're at least consistent, because these reviews are awfully similar. So I am telling you, the memory is not only I sent him a review and I forgot, but then I read the paper and I forgot that I had read it before and I sent the review. But as he said, I was happy that I was consistent. And what I didn't like the first time, I didn't like the second time. So that's as far as memory is concerned. But okay, so let's get back to here. So Vishkin claims that it's possible to construct a sample of size log m, but for non-periodic patterns. So he says this kind of a property, in fact, holds for a sample of very small size. The size is going to be logarithmic in m. So the sample is going to be of size log m. So that's okay. We can do that, he says. But not for every pattern. Only for non-periodic patterns. So now we need to know, what does it mean for a pattern to be periodic? So let's look at the definition. We're going to say that a string, or in this case a pattern, but a string P is periodic if it can be written in the following fashion. If there is some substring u, such that P is equal to u concatenated by itself v times, followed by some prefix of u. And this v has to be greater than 1. At that point, we say that u is a period of P. So that's what a periodic string is. And let me also caution you that this is the computer science definition. The mathematicians define it a bit different, and we're going to actually look at the way mathematicians define it in a minute. But computer scientists, okay, the main difference is that when mathematicians are concerned, this is not v greater than 1, but v greater than or equal to 1. So as far as mathematicians are concerned, A, B, C, D, E, F, G, A is periodic because you have A, B, C, D, E, F, G followed by an A. Computer scientists will say it's not periodic, but A, B, C, D, E, F, G, A, B, C, D, E, F, G, A, that would be periodic. And also A, B, C, D, E, F, G, A, B, C, D, E, F, G is periodic. So computer scientists would like the period to appear twice. Mathematicians say it doesn't matter. The period is there, and the prefix of it, that would be periodic. There's not going to be that much difference, but it's something, it's one of these little cultural things that are there. So let's see as an example. So ABCAB is not periodic by computer scientists. It is periodic by mathematicians. ABCABCA is periodic as far as computer scientists are concerned. But now, let's look at A. So we're looking at this one. This particular string is periodic, that's for sure. But when I say that U is the period, well, this string has a number of periods. So it has this period, ABC, 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 because that repeats and then starts. Okay, it also has another period, ABC, 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 because this one appears once, twice, and then it starts. And it also has, that's period 2. It also has this period, ABC, 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 A. And it even has period 4. Which is this one, ABC, 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 A. Okay, so it has a bunch of periods. Now, what we're going to need is to understand a bit about these periods, and we're going to understand it by Feynman-Wolff's periodicity lemma. Now, Feynman-Wolff were mathematicians, so their periodicity is a mathematician's periodicity, not a computer science periodicity, but they allow us to, in fact, talk about the period of a string. Because if we, as we saw, there are many periods. So what does it mean, the period of a string? So Feynman-Wolff say the following. If U1 and U2 are periods of string P, and let's say that the length of U1 is x1 and the length of U2 is x2, then P has a period U3, where U3 is the greatest common divisor of x1 and x2. Now, if we go to the example that we saw before, we see that that's what happens here, because we have this period, whose length is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have this period of length 12. We have this period of length 9. So that would be period 1 of length 12, period 2 of length 9. What's the greatest common divisor of 12 and 9? 3. Okay? So 3 divides 9 divides 12. No larger number divides both 9 and 12. So it means that there is also a period of length 3. And there is. That's what we called period 4, ABC. ABC has length 3. Now, this is fun. And it's also cute. But it's also important because what it means is that if you have two periods, take their greatest common divisor. And then if there's another one, take the greatest common divisor. Keep taking the greatest common divisors until you get to the smallest one. It is going to divide all the periods. And so they are all going to be basically multiples of the smallest period. Okay, you can also take the period to be the longest string that repeats. And sometimes it helps. In fact, I don't know, we wrote a number of papers where we did that. So that's a period. And so if you look at the longest string that repeats, that's fine. But if you want to define, you could define it as the longest. But it's actually, in some sense, more basic to say, let's look at the smallest. And so the point is that there is a smallest. There are no two different ones that are both the smallest, because then there would be a period that is even smaller than both of them. Or one of them would divide the other. But there's always a smallest one that everyone else is a multiple of that smallest period. And that's a very important observation. So this is Feynman-Wilf's periodicity lemma. So when you hear people say the periodicity lemma, this is the one. So let's look at the proof. Okay, is the lemma clear though? Any more questions? Because so far today your observations have been great. So if they don't have a common divisor, let's say, yeah, so if I have a period of length 2 and a period of length 3, then it was AA and AAA. Now, in some sense, okay, so the periodicity lemma is one of these things that when you deal with it, it's like it gets so much into your blood that you don't even think that it could be anything different. But sometimes it helps, because when I see it through fresh eyes, I say, well, why? Why is that? So, okay, so let's see why it is. All right. So for the proof, as I said, Feynman and Wilf were both mathematicians. So we're going to prove this for periodic strings of length in a mathematical sense. So V is greater than or equal to 1. Okay. And so Feynman and Wilf said, okay, that we defined the periodicity. Okay, and we said that the period repeats, and then there's a prefix of it. But there's an alternate view of it. You can also define it differently. So if the length of P is M, and if the period length is X, then for all I between 1 and M minus X, P of I is equal to P of I plus X. Okay, so look at it a minute, and you'll realize that it is really an alternate definition of periodicity. Because what does it mean? It means, okay, you take the first element, X away, it's the same. You take the second element, add X, it's the same. You take the third, X away, it's the same. So it's a period of size of length X. So that's the period size. So that's another definition, and with this definition, it's going to be easy for them to prove what they prove. Now we also need a couple of algebraic conclusions. Or not algebraic, but basic number theory conclusions. The first one is, if B and C are co-prime, meaning the only divisors they have is 1, the only common divisor. Then B minus C and C are also co-prime. And that's without loss of generality. We're assuming that B is greater than C, of course. Because B minus C, we want it to also be non-negative. Well, if they're the same, they're not co-prime. But OK. So let's see why this is true. It's true for obvious reasons. I mean, let's assume that B minus C and C are not co-prime. So B minus C would be x times W, C would be x times Z, and x is not equal to 1. That means that they're not co-prime. They actually have a factor that is not 1 between them. OK, well, then what is B? B is equal to B minus C plus C. So that's equal to XW plus XZ. And if you open it up, you get x times W plus Z. W plus Z is not 0. So here you are now. X is actually a divisor of B and C, because this is x times Z and this is x times W plus Z. So that contradicts the coprimality of B and C. Therefore, B minus C and C are also coprime. Okay? Now, as a corollary of this lemma, we can get that the greatest common divisor of P and Q is equal, for P greater than Q, is equal to the greatest common divisor of P minus Q and Q. Why is that true? So, again, let's look at P. If P is equal to AB and Q is equal to AC, and let's say that A is the greatest common divisor of P and Q, which means that B and C are coprime. Okay, so that's so that would be the greatest common divisor of P and Q would be A. Now, P minus Q is going to be equal to A times B minus C. And because P was greater than Q, then this number is actually non-zero. Now, B minus C and C are coprime. And that's the lemma that we just proved. So, because B and C were coprime. So if B minus C and C are coprime, then what do we know about A? That it's the greatest common divisor of Q and P minus Q. So because of that lemma before, we now get this. So what we need to remember is that the greatest common divisor of P and Q is equal to the greatest common divisor of P minus Q and Q. Now, what do they need all these things for? You can imagine, because since they want to show that the greatest common divisor of two periods is also a period of the string that we started out from, and one of those periods is going to be longer than the other period, so you know already where the P minus Q comes in and where the greatest common divisor is going to play a role. So let's, now that we have all these facts, these fun facts, let's return to the proof of Fine and Wolf's lemma. And we're going to, yeah. Yeah, I have to come close because this air conditioner is sitting on my head and going, woo. What you're saying is, what happens with two-dimensional periodicity? Well, two-dimensional periodicity is actually a topic in and of itself. Two-dimensional periodicity did play a role in some algorithms for two-dimensional matching, and certainly played a role in compression of two-dimensional, but it doesn't have unique definition. There are various ways to define two-dimensional periodicity. Both mathematicians and computer scientists have looked into it and have done work on it. So it's a big topic, but it's not as simple as one-dimensional. Okay, so this one we're going to prove by induction on the length of our string, on the length of our pattern. So here is one of our beloved proof techniques, mathematical induction. Okay, so the the lemma is clear for p of length 1, because if the length of the lemma is 1 and there is 2 different periods, well, who can be the periods? It doesn't even have any periods, so it's obvious by vacuously. So for p equals 1, it's obvious. So let's assume, and by the way, if you want to take one more step for p equals 2, it's also quite clear, because that would only be periodic if it's AA. So the period, there's only one period possible, and so if U1 and U2 are periods, then obviously the greatest common divisor, which is 1, is going to be the period. So this is clear for the small cases. So let's assume that the lemma is true for all strings of length less than n, and let's prove for p equals to n. Okay, so here is p, and p has one period u1, and it has another period u2, and in this particular case, because I don't want, I want it to be not trivial, I even drew them so that they don't end up together. So it's like the case of the 12 and the 9, for example. So this is the most general case that you can have. So you have period u1 and you have period u2. So let's look at the u1, and what does that tell us? Well, u1 itself, because u2 is the smaller period, so we assume without loss of generality that u2 is the smaller period. So because u2 is smaller than u1, then it must be also a period of u1. There, again, we're looking mathematician definition. So it's a period of u1, and if it's a period of u1, then u1 of I is equal to u1 of I plus x for all the i's between x1 and between 1 and x1 minus x2. So this is because u2 is actually a period of u1. And it has to be, because u1 is a period of p and u2 is a period of p. So as you can see, u2 is a period of u1. And therefore, that is true. Okay. Now, but u1 is a period of pi. So pi is a period of p. So pi is equal to pi plus x1. But p also has a period u2 of length x2. So therefore, pi plus x1 is equal to pi plus x1 minus x2. Why is that? Because if you look at I plus x1 minus x2, you add to it x2, you get that. And x2 is a length of a period of p. So therefore, it's true that pi plus x1 is equal to pi plus x1 minus x2. So far, and that, you figure it out, it's for I of, by definition, between 1 and m minus x1. So all of this we know so far. So what do we have? We have that pi is equal to pi plus x1. It's also equal to pi plus x1 minus x2. Wait, yes. So we can conclude from that that u1, in fact, has a period of length x1 minus x2, because if u1i is I plus x2, pi has this. Now u1 is actually a substring of pi. So within u1, this also holds true, that in u1 I plus x1 minus x2 is equal to u1i. So it means that u1 itself also has a period of length x1 minus x2. Now, this is good because u1 is already, since it was a period of p, so u1 has a smaller length, and now we can use our induction. So u1 itself, we know what to say about it, because it has a period of length x2, and it has a period of length x1 minus x2. So by induction hypothesis, it has a period of length the greatest common divisor of x1 minus x2 and x2. So u1 has both of these periods. By the inductive hypothesis, it has the greatest common divisor of those guys. Now, the claim said that the greatest common divisor of x1 minus x2 and x2 is actually equal to the greatest common divisor of x1 and x2. So what does it mean? It means that the period, this subperiod of u1, because its length is the greatest common divisor of x1 and x2, it actually divides x1, so you can write it like this. So that subperiod actually ends up in the border of u1 because its length is the greatest common, it divides u1. So that's where it ends. So the picture, in fact, looks like this. This new period that we have, unlike u2 that didn't end up on the border of u1, but this new period does end up in this border. But, okay, but at this point we're done. Because if the period of whose length is the greatest common divisor x1 and x2 actually ends here, then concatenate this period to itself. Concatenate it to u1 again, and to u1 again, and then to the beginning of u1, and that's p. So this little period of length GCD x1, x2, in fact, it's a period not just of u1, it's a period of p as well, because it divides u1. So it ends up there, you can just concatenate it. So it's a period of p. And that proves the Feynman-Wilf, the periodicity lemma. Okay. So now we're back to Vyshkin's algorithm. So Vyshkin says, take your pattern and assume that your pattern is non-periodic. Now, take the pattern and consider all the shifts and stack it on itself, m over 2 times. So this is your pattern. You're going to shift and stack, shift and stack, shift and stack, up to m over 2. Now, the pattern, so far, we haven't done anything, okay? We took the pattern, we shifted it, we stacked. Now, the pattern is non-periodic. That he assumes. And we'll see at the end what he does with periodic patterns. But at the moment, the pattern is non-periodic. So he says that there must be a column that has at least 2 different symbols. Why is that the case? I mean, assume that all the columns between here and here, they're all the same. I mean, if there's an A here, it's an A all the way. If there's an A here, a B here, it's a B all the way. Okay, assume that that's the situation. But if that's the situation, then what do you know? If there's an A here, it's an A all the way. Okay, so it means that this is equal to this. So if there's an A in position 1, then there's also an A in position 2. And then there's also an A in position 3. And then there's an A in position 4, all the way in to position m minus 2. But then, because m minus 2 also goes all the way down, it means that all of these are A's all the way. So this can only happen if your pattern is all A's, that there's no column with 2 different symbols. And if the pattern is all A's, it's obviously periodic. So if the pattern is non-periodic, there must be some column that has more than 1 symbol in it. Yes, but we're going to need to assume non-periodicity for later. Because this is just the first step. Okay, so this is the first step. So there is a column that has at least 2 different symbols. So let's choose some column J where the symbol A appears less than half of the times. Now, in fact, if you have some column where some symbol appears only once, you'll choose that one and you'll be happy. But the point is that may not happen. But since every column has at least one element, then there must be at least one column where some symbol occurs less than half of the times, or maybe even the same, exactly half of the times. It doesn't have to be less than or equal is also okay. And so we're going to discard all the rows where A is not in that column. And now we have a smaller stack. In fact, we have a stack that is maybe half the size of before and maybe even smaller, because as I said, if you found a column where there's a symbol that appears only once, then discard everybody except for that particular row. So now we have a smaller stack. We're going to repeat until only one row is left. And here is where the periodicity comes in. But let's look at an example, and then we'll see why the periodicity helps also in the cases of when some of them blew out. Okay, so let's look at this example. Suppose this is our pattern, ABA, BB, AA, BAB. So we stack it on top of itself here up until the half, and then we pick a column. So let's pick this column here. We have A's 3 times, we have B twice. So so we pick the B, and we discard everybody else. So who's left? These 2 rows are left, this one and this one, because everyone else we throw away. So we're left with this. So now let's pick this row, where you have different symbols in different locations, and let's pick the symbol A. And at this point, we're left with this. Now remember that this guy, we also keep where it was before. This guy had the B here that we chose, and it has the A here. So this guy that we chose has A here and B here. And the fact of the matter is that that's going to be our sample, okay? So the sample is going to be the 7. In the 7th position, we want an A. And in the 8th position, we want a B. So that's going to be our sample. But the point is this. If you go to a particular position in the text, and you look for A and B in locations 7 and 8, because there was only one element left from this entire thing with locations 7 and 8, it means that, in fact, and it was this one, it means that, in fact, all these starts from here to here have been canceled. They're all in the dead zone. So you cannot have this and this. You can't have this and this and this and this. The only thing you can have, if this is the sample, is this row, because this row is different from these 3 rows here, and it's different from this row here. So they all die. So your dead zone is from here to here. In fact, since only one row remained in M over 2 area, so your dead zone here is M over 2. So C is equal to 2. It's a big dead zone here. But the question is, how? Okay, so I think that the numbers here are calculated. So so any position I where 7 is A and 8 is B cancels all the options from I minus 1 to I plus 3 except for I. So that's the dead zone. Now, what's the size of the sample? Log M, because what happens? The first element that you took occurred less than or equal to M over 2 times, so half of the elements were thrown away. The second time, half of the remainders was thrown away. So that's a quarter. The third time, an eighth was thrown away until you get to 1. So even in the worst case, if there's always exactly half that you throw, in log M iterations, you're down to 1. But this is why I said that what you should do in real life is look for the column that has the smallest number of repeating symbols, because then you may gain. So if there was one column where there was a single A, then your sample is going to be of size 1, and you can finish. So suppose, for example, you had a pattern where you have a bunch of letters, but the letter X appears exactly once. So you take X as your sample. And anywhere where you find an X is an option, but because if you find an X in a particular position, and it only occurs once in the pattern, then it kills off m over 2 options every X you find. Now, the beauty of that is that it may very well be that you find another X close to this one, and at that point, you kill off even the original element. You can also do something else. You can also run, find your element, I, see that the sample holds. Let's say that X, it was one element. See that the sample holds. Run all the way to the end of the kill zone and don't even bother to check anything else, and check for X again, and run to the end of the kill zone and check for X again. At that point, your algorithm just for finding the candidates is going to be n over m, O of n over m, the algorithm for finding the candidates. So, and if there are less than that candidates, then your verification is also going to be smaller. So you have an option of actually being less than linear time even in this algorithm. But in the worst case, the algorithm is going to be log n for every location, and then you kill off the dead zone. So at the worst case, this algorithm is going to be n log m. Also, you notice that the algorithm is easily parallelizable, because all you need to do, and it's going to run in time log m, because all you need to do is for every location check the log m, and then get rid of everything in the dead zone, and then even if you do brute force, because they're far enough away, your time is going to be basically O of 1 for doing the checks. So the sample size is O of log m, and that's because at every iteration at least half of the rows are eliminated. The question is, what happens with periodic patterns? There's also something else I have to tell you. Why are we guaranteed even after the first? Okay, so we said why in the first time, if we have a row, we're okay. But why are we guaranteed that there must be a column with more than one symbol even in the second time and in the third time? Maybe then we're not going to have it. Maybe then all the columns we have are the same. Okay, so think about it. This is also something that comes out from the traits of periodicity. If you have a string S and you have another appearance of the string S over here, and if the columns are equal, even I'm talking here even about two occurrences of S, and if the columns are all equal, it means that this is equal to that. What does it mean? Okay, we're talking here about something that is closer than m over 2, right? Because that's where he puts his strings. Now, this is actually one of the basic things about periodicity, that when you get used to thinking periodicity, you look at that and right away you're going to yell. But if I can shift a pattern less than m over 2, and it's the same, and it coincides, what can I say about that pattern? So look, this is equal to this, right? And this is 1, so that's equal to that. Let's say 1. This is 2, and it's equal to this. So this is 2. 3 is equal to this, so this is 3. And then it goes on. 1, 2, 3, 1, 2, 3, 1, 2, 3, okay? So what do we get? It's periodic. So one of the things that when you're comfortable with periodicity, you see a string and you say, well, I shift the string less than m over 2, and it's the same, right away you, in the middle of the night, you say, ah, yeah, it's a periodic string. So it cannot be that even up to 2 strings, that you have a non-periodic string and everything is going to be the same. It's not going to happen. Okay, so now that we have proved the algorithm and we've established everything, let's now just say the last thing. So this is all good if your pattern is non-periodic. What do you do with a periodic pattern? This idea is not going to work. Well, the log is going to be even smaller, because if you have a periodic pattern, look for the period, the smallest period. Find for the smallest period its sample, and find all the locations where the smallest period exists. And once you're done with that, just make sure that you have a large enough sequence of the occurrences of the small period to have the original pattern. So the time is still going to be the same, not going to be any change. You can still do it all in parallel. Everything is going to work out, but you handle also the periodic string. So the idea is your sample, and the sample obviously is going to be smaller if you have a smaller period. But the idea is you have a sample, the sample is deterministic, and no matter what, it clears up the dead zone for you. So this is Vishkin's algorithm from 1990. I wish you all a happy weekend, and we will meet with invigorated and fresh on Sunday at 9, I assume, right?